it's a pleasure for me to present this talk about attacks and trust in connected networks. So I start the presentation by introduction, and I give the motivation and some of the limitations of existing works and some of challenges facing the industry and the academic community regarding the problem that I will mention. After that, I will describe some of contributions we did in our laboratory regarding the attacks problems in connected networks. And I conclude the presentation by some potential axes that can be useful for collaboration with the SystemX. So the technologies of connected networks today are attracting several applications and many applications in our daily life. The connected network technologies are everywhere and anywhere. We can mention, for instance, vehicular networks. We find also connected networks in smart cities applications, in ad hoc and in ad hoc networks, in also smart grid, etc. So what we mean by connected network? The technology of connected networks means that the devices are connected in a wireless manner without requiring central entity to be like a central management element. So usually these technologies are characterized by the wireless medium, and all wireless devices using these technologies are connecting via wireless medium. Also, these technologies are characterized by the absence and the lack of the central point. We don't have like a central point to manage and to control the whole infrastructure communications. And the other characteristic is also the dynamic nature of traffic within the connected network technologies. So these technologies are really very powerful in terms of applications, in terms of case uses, but they are very vulnerable to attacks. So why they are vulnerable to attacks? So I can mention three factors or three reasons, three main reasons leading to say that this technology is very vulnerable. So the first issue is that these technologies are characterized by multiple interfaces, and these interfaces are usually wireless. This means that, for instance, in a connected vehicle, we can put like a wireless card in type of IEEE 802.11p. We can also put another one to communicate with ZigBee networks in the roads. We can also put another wireless cards to communicate with 5G, with LTE, with 5G and beyond, etc. So we can find like heterogeneous wireless interfaces within one wireless connected device. So and we know that each technology and each wireless medium has its own characteristic and has its own limitations and vulnerabilities. So this means that the connected wireless technology will inherit from the limitations and from the vulnerabilities of all these technologies. The other issue is that the connected network technologies are characterized by their limitations of resources and the complexity of embedded systems within the infrastructure. So this means that we cannot deploy like the concerning algorithms in order to ensure like enhanced security. We cannot deploy like a deep learning algorithm in order to ensure the detection of malicious activities, etc. So we have to put central attention and special attention to the resource limitation factor within the wireless network, the connected wireless network technology. So the other factor is also that this technology is characterized by the absence of central trust authority. This means that we don't have like central point in order to ensure or to guarantee the security and the trustness and the reputation of the whole devices within the infrastructure. The network is distributed, and this means that each node has to pay attention regarding the reputation and the trust of the others. So, given all these reasons, we can say that this technology is really very vulnerable to attacks. This technology is inheriting all the traditional risks and vulnerabilities coming from the traditional Wi-Fi, from the traditional Zigbee, from traditional Bluetooth, etc. So, but what is the consequence of this? The consequence is twofold. So the first one is in terms of privacy. The vulnerabilities within the connected network technologies will lead to the violating the privacy of users. For instance, one attacker can follow your all actions you do from the morning to night just by following your movement or the movement of your vehicle. So the second consequence of these factors is the attacks. And like for instance in vehicle network, we can imagine that the attacker can integrate false messages, can integrate false data, can inject false information, etc. within the network. So this means that this kind of technology is very vulnerable, and we have to pay attention when we conceive models to ensure both privacy and security. So yeah, this is this is a photo that I've taken from this reference. It represents the card, to represent an attack that has been done on Jeep model a few years ago. So yeah, there are a lot of research done in order to ensure the security of wireless networks, and also there are also several works regarding how to enhance the trust in mobile networks. But to my opinion, there are a lot of challenges for the scientific community in order to enhance the both privacy and security regarding the connected network technology. So one of these challenges that faces the scientific community is how to deal with the end-to-end detection. So the majority of works in the literature deals with the detection in local domain. For instance, in mobile networks, we try to detect attacks like in just one segment of the network, in the last mile of the network, but not in end-to-end manner. So another challenge is also associated with the nature of attacks of today. So today, with the invention of 5G, attackers can use mobile networks in order to push attacks with a rate of 1 gigabit per second just by one device. Imagine that we have 10 devices that have, like in theory, like you have data rate of 1 gigabit per second. This means that we can attain 1 terabit per second in terms of transmission, and in terms also of reception by server in just 1 second by using just 10 devices. So this means that the attacks today is easy to do because the capacity of wireless devices becomes more and more higher. So the other issue also facing the scientific community in order to propose an innovative security and privacy models in this regarding this technology is the scalability issue. A lot of works are dealing only with small set of devices, but when this kind of solution is experimented in real use cases and experimentations environments, so we face the problem of scalability. I think the scalability issue remains one of the major problems regarding the deployment of efficient cybersecurity solutions in connected networks. The other one also is related to the end-to-end, but in terms of layers. So we know that the majority of works are dealing, for instance, with layer 3, how to ensure the security of wireless routing, or how to secure routing within the network. But if the layer 3 is like very secure, but layer 2 is not secure, this means that the model we propose is not really efficient. Because an attacker can monitor the parameters that usually we have in the IEEE 802.11, for instance, like the backup range, backup windows, etc. So what does mean that if you have like a very extended routing, security routing in layer 2, in layer 3, but you have like a very vulnerable medium access control model. So I think that the end-to-end layers and the end-to-end from the user to the end user, both should be integrated in order to ensure like efficient security philosophy and approach. See, the other challenge also is how to build a bridge between the industry community and the academia community. We know that we are researchers and we develop every week, every month, we develop new works regarding the cybersecurity. But the question is only this innovation, what I did in my laboratory, is it only efficient in terms of industry? So I think that the collaborative work between the industry community and the academia community is the key for the success of innovative security solutions in the future. Particularly in technologies like V2X and technologies like e-health and e-medical solutions, etc. So the efficiency of solutions will be like tested when we deploy it. And the bridge between the industry effort and the academia innovation, to my opinion, will be the key of success of the security solutions. So I will present you here some of our contributions we did previously. So I start by the one contribution that I did jointly with the University of Montreal. It's like a joint work between Canada and France. In this contribution, we dealt with the issue of DDoS attack detection and mitigation. What is DDoS attacks? DDoS attacks is distributed denial of service attack. In this attack, we have like an attacker who like takes control of several devices, what we call a zombie, and that we can also be a bot. And all these zombies will float one target. by sending like a heavy message, etc. So we have several ways in order to achieve DDoS attacks. But the global philosophy is just to flow the memory and resources of the victim in order to put its service like out of service, will be denied. So in this work, we propose a scheme in order to deal with the DDoS attacks detection, attacks in end-to-end layer from IoT device to the cloud device, using a multi-layer and end-to-end philosophy. So in our work, we considered SDN and vision. You know that in SDN, software-defined network, you know that you have three layers. You have the data plane devices or plane, the control plane, and the application plane. All these planes are separated, and this is like a future view of networking. So in our work, we consider that we have like a data plane here, a set of devices, and we have a controller, the blue devices here, and we have like in the upper layer, we have an application layer. And we try to follow the attacker from the destination to the source. So for this manner, we propose two approaches. The first one is to deal with the intra-domain detection. We try to detect the issue here or malicious activity here. And after that, we try to follow the attacker, because maybe the attacker is not here in this domain. Maybe the attacker is located somewhere here, outside of the domain. So in the second step of our solution is focused with the how to detect or how to follow the attacker till the source. So let's start by the first step of the mitigation scheme within the same domain. So in this study, we considered four attack scenarios regarding the DNS server and the attacker. So you know, in the literature, we can find these four scenarios. The first scenario is when the attacker is located outside of the area, and so both the attacker and the DNS server are located outside of the network. So in this scenario, attacker try to launch and to send like DNS request, and the DNS server here, and the DNS server will send the response to the victim here. So why? Because the attacker has spoofed the DNS request queries here, and the attacker here puts the address of the target as the destination. So if there is no way of securing this scenario, this means that the DNS server will send all the responses to the victim, which is located inside the network. The second scenario is is when the internal attacker and internal server here, the external attacker, and the internal server. This means that the attacker tries to send a DNS query to the server, and after that, server will send the response to the target located within the same network. And after that, we have the problem of what we call DNS amplification attack. This is also one way to achieve a DDoS or the distributed denial of service attack. The third scenario that we consider is when the internal attacker and the internal DNS server are located in one network, as we observe here. all the devices are located within the same network. And this is like the very simple case where the attacker can, in a simple way, can falsify the DNS queries. The fourth scenario is when the DNS server is located outside and the attacker is located inside the network. Here also, we did experiment and we find that the attacker also can easily can easily spoof the DNS queries to the server, and after that, server generate DNS responses in an amplified way in order to to put or to generate DDoS distributed denial of service behavior within the resource of the target. So in order to deal with all these schemes, so we proposed in the at the first element of the first step, we proposed a scheme that we call it proactive and stateful scheme. So this is like a physical reaction to the queries. Here, this algorithm, we mentioned that when server receives, for instance, here, when server receives a query from the network, from the device, so it has to check the type of the DNS packet, because we have several types of DNS.
Ça dit le contrat actuel, il ne prévoit pas.
Yes, we have several types of packet DNS. We have copied in the past.
Yes. May I interrupt you because we do have some echoes from your side, I think?
No, not from my side, no.
All right, can you please, for all of the listeners, can you just mute your microphone, please? Thank you. Go ahead. Sorry.
Yeah. So what we did, and after that, we have copied and passed all fields from the DNS response that we want to generate within, and we copy it from the previous one. For instance, we put the destination in the source and the source in the destination, etc. What does this mean? This means that we will have like some action like that. When attacker will send DNS or query to the network, so the network will not check the destination address here, but the first element to check it is the physical port number, and within this we will respond using this same port number. This means that if attacker will try to spoof DNS query, the network server will send him the DNS responses, and after that, the attacker will be flooded by himself. And the attacker here has no any useful consequence to this. The attacker here will flood its memory and computation spaces. So in all, we have tested this with all scenarios, and we proved that by using our scheme, the attacker always will receive the responses based on the request sent by himself, by the attacker. So after that, once we did what we call the mapping of one-to-one, this process that I described before, is called the mapping stateful mapping one-to-one. Once this step is achieved, we'll try to collect the some informations regarding the flow states, like the number of packets and other informations. After that, we'll compute the entropy, and after that, we'll use the Bayesian filter, and after that, we'll try to classify the flow whether it's an attacker or not. So as you can see here, so the path, this is the first state, or the first element of the first state. This is the mapping state for scale that I proposed before. Is deployed within the OpenFlow or Open switch, and and the Bayesian and the others one and other applications here, the entropy, etc., is deployed within the rest or within the application layer of the SDN. So I don't know where is the algorithm here. So yeah, we proposed machine learning that which combines the computation of entropy and the Bayesian filter in order to classify at the end even the flow is characterized as illegitimate or not. So by using BNF, like very simple Bayesian filter, we have only two classes, and these classes are based on the output of the entropy, and the entropy is based on the number of packets within the same flow. So the results of our work have been published in this review, HRP transactions on network and service management 2 years ago, or 3 years ago, and we observed that when we apply our entropy and our stateful mapping and Bayesian filters, etc., we observed that the number of packets within the controller will be reduced to like one reasonable level. And after that, even an attacker tried to push more other flows and more other packets. We observe that the peak here doesn't exceed one threshold we fixed before. And so all the steps is when our controller is disabled, when we don't activate our controllers. But once we activate it here, so all the peaks or the amount of traffic we observe within all devices and all controller within inferior to one threshold that we fixed before. So this is like just the global view of one of our contributions we did in order to classify an attack and to study the malicious behavior within one same domain. But as I explained to you, the issue is here. The issue is what's happened if the attacker is not really originated from here, from this domain? What's happened if the real attacker comes from another domain, very, very far from us? So in order to follow the activity of the real attacker, so we propose to use and to deploy a blockchain and smart contract within the application layer of the SDN, and where we deploy the contracts and the smart contracts on all controllers. So we, in our work, we once the SDN controller of the victim domain detects the attack, using our previous scheme, and we classified this. We classified the flow as like it is not legitimate. So we have to report this information within the smart contracts, and we send and we report the IP, the suspicious IP address within the smart contract. When we report this information here within the smart contract using Ethereum in our case, this information will be propagated in all smart contracts clients, because all smart contracts clients are supposed to get the same information of what we have in our smart contracts. Once we report the behavior of the malicious IP address within the one controller, this information will be broadcasted within all smart contracts of all other control planes. And for instance, if the real attacker is this one, this information will go to this smart contract, and after that to this contract also. And the controller here, the SDN controller, will say, yeah, this address belongs to my domain. And after that, our controller can block this device or can take another action. So you can take any scheme from the well-known reaction systems that we have in the literature in order to deal with this step. But like very one simple reaction is just to block the IP address here, to block this device, for instance. So we computed the price of all activities and the actions we do in order to create the action within the smart contract, in order to delete this action, etc. We computed this, and we deployed our smart contract. This is the website of our results, and this work regarding how to follow the attacker till the source has been published in the IEEE Access a few 2 years ago. So let's go now to another contribution that we did, and in this work, in this second work, we tried to do the same thing. We are trying to propose a multi-layer and end-to-end security model from the source to the destination. This means from the IoT device till the layer of the cloud, for instance. And this is the global scheme of this second contribution. So we started this model by collecting data, by collecting log files, etc., from IoT devices, from machines, etc. Once this data are collected, we apply a data classification scheme, and once this is classified, so we activate another module that we call Markov chains. So by activating the blockchain, the Markov chain, sorry, we can predict the next or the future states of the device, given the real only the current states. So, and once this work is done, and once we ensure, or that like we are very sure that the next step, such a device will be like an attacker, will have like an attacker. So we have to take an action, and our action is realized by a specific reaction module, and inside we implemented also a smart contract. So this work, this second contribution is based on end-to-end layer from IoT devices. When I say IoT layer, this means, or access layer, this means that we have sets of heterogeneous networks like IoT devices, industrial IoT devices, smart home IoT devices, etc. All these IoT devices are connected to the MAC layer via access points, via, for instance, 5G ports, and these devices and or this information will be analyzed here at the MAC layer, and after that we'll take action and we'll report the information within the cloud. So in this approach, we considered that we have like 3 behaviors. This is very classic. Even in the access control security layer, we know that, for instance, in access control, once the person or the agents or the device has been authentified, so we have to pay attention to the step next. What is the next step after authorization, after authentication? The next step is the authorization. We have to pay attention to what kind of resources will be accessed by such device once will be authentified. So our model will help in this like security service that we call access control security service. So in our case, we consider that each IoT device have like 3 behaviors: authentic, suspicious, and malicious. And we consider that each IoT device can take some of the actions. For instance, if the action of the IoT device is to delete some resource within the server of the company or in the cloud, etc. So in our algorithm, we characterize this activity like a malicious activity, because the device has no right to delete some resources within the remote server. So if this happens, we will report this, and we will block the device. We will report the information within the cloud, within the smart contract also, and we will update the list of our blacklist IoT device. So if the activity of the IoT device, once this device has been authentified, is not associated with like deleting resources, etc., but other action like reading some remote resources or trying to modify some information, but not delete. So in this manner, in this step, we will activate our Markov chain stochastic process. And our stochastic process model will tell us if the activity of the IoT device in the future will jump from the suspicious to malicious, or from malicious to authentic, or from authentic to suspicious, etc. So in our work, we considered like we have 4 ranges. So each device can take one of these activities, like authentic, low risk attack, medium risk, suspicious behavior, and malicious behavior. So the malicious behavior is here, the malicious activities are here, and the authentic case is here. So we developed the state transition diagram considering the all activities. When the IoT device tries to delete something, it will be in this case of delete, and it will be like it will be broken. But if the device tries just to read we follow its behavior using the Markov chain process, and maybe we go from the range 1 to range 2, and from range 2 to range 3. If we say that in the next state our device will behave like an attacker, it will be stopped and will be blocked, and we will put this information within the cloud with the blockchain smart contract. But if the device just to modify the information, so we will not delete it, we will not block it, but we have to follow its state within the future. So we computed the probability of transitions. We computed the stationary probability and the stationary distribution, and after that, as I mentioned before, once the Markov chain has been activated in order to tell us the behavior of the next state of the IoT device, we have to report this information, and we have to report it within the smart contract. So, but why we have to report this? In order to react. In order to react. So we proposed several reaction algorithms, and each reaction algorithm trying to follow the information. Try to follow the behavior of the IoT device from one state to another state, etc. And for each, once the behavior will be like here, like a critical situation, we have to block the device. We proposed several reaction algorithms, and after that, we realized simulations using the well-known accuracy error rate parameters, the detection rate of intrusions, etc. And we compared this with the traditional work, and we observed that our work enhance the results, and our work gives more interesting results when compared to the traditional network or the traditional admission control states without any security given. So these works have been published in the IEEE Network magazine and also in the IEEE Transactions on Network Science and Engineering. So the reaction and the Markov chain and the smart contracts have been published here. The IEEE Network magazine and the Markov chain with the all mathematical formula, etc. has been published in this work. So I will.
Yes. If you allow me, just maybe before jumping to the third contribution, you do have 5 minutes. If you can conclude, please, to let people ask questions. Yeah. Okay. Thanks for understanding. Yeah.
Okay. Very sorry for that. So maybe I will jump directly to the. I will jump directly to the. So in another contribution, we proposed also a privacy. We are proposing some models based on federated learning in order to ensure privacy in IoT devices in cloud also. So I'm here in the conclusion. Very sorry for this delay. So we are working in our laboratory to propose models to enhance the detection and also the prediction of attacks, and to study the behavior of malicious activities within a set of networks like the IoT, industrial IoT, in B2X, in SDN, and I'm really open to start new collaborations with SystemX, but also with all audience in these areas of research. And so again for the delay. Thank you very much.
Thank you so much, Lyes, for your nice presentation. The floor, if you have any questions, just activate your microphone, please, and go ahead. Don't be shy. Okay, maybe I am going to start by asking a question concerning the slides 18. If you can go back, please. Yeah, you mentioned the notion of entropy. Am I right?
Yeah,
Yeah. Could you give us more detail, please, on how this entropy is actually calculated within this process?
Yeah. So the entropy here. Yeah, I think that was. Yeah. So the entropy, the first step, we have characterized what is the flow. The flow, in our case, is set of 7 information: the IP address, source, the IP address, destination, the type of the traffic, the port number of the source, the port number of the destination, etc. We have considered 7 information.
Yeah.
After that, we computed the number of, in average, we computed the number of packets of one flow, and after that we achieved the traditional formula of how to compute the entropy, and we normalized also this. Once we have normalized this, we obtained a vector of 3 informations, like the entropy before normalization, after normalizations, and one another information. So this vector will be the input of our Bayesian filter. After that, we computed the probability to go from or to get the probability that this vector it will be to say that is legitimate or illegitimate if this probability is superior to 0.5, we consider that the behavior is considered like illegitimate, not legitimate. If it's inferior to 0.5, we consider that this behavior is legitimate. So this is like, but another one, for instance, here we can imagine that in place to consider only 2 categories here using Bayesian filter, so we can improve this work in order to create several classes.
Yeah.
Using another machine learning algorithm, we can use, for instance, fuzzy logic in order to put several classes, etc.
Okay, I see. Thank you. Questions from the floor?
So as I told you, if you want to work in all these areas, so I'm really very happy to start collaborations.
Yeah.
So in all these areas, like V2X, like SDN Cloud, in IoT devices, we have several works.
Absolutely, yeah. I was thinking on that also. Maybe we take the question of Yorina Gonzalez. Go ahead, please.
Yeah. Okay. Thank you. Thank you very much for the presentation. Now, I have doubts in my research. I have problems with data sets. So I don't know if you managed to deal with how you managed to get data to test the contributions, because especially when working with Internet of Things devices, it's quite difficult to collect a real huge data set to provide meaningful results. And obviously the protocols can be terribly good, but the problem is that if we cannot test it in a real environment, then we miss something about performance. I mean, we don't miss, we miss the measurement of performance and so on. So I don't know what your insights in this regard.
Yeah. So thank you very much for this very good question. So yeah, one of the major challenge here in our research is how to get real data set. And so we started our research a few years ago by using like very common and public data sets like ENSICAEN and ENSICAEN, developed by the Australian Institute of Cybersecurity and the Canadian of Cybersecurity Institute. You know, their data sets are very well and very common. But in some use cases of industrial IoT, we are trying to use like not really our data set, but we are trying to generate some random data set, some data, and we are doing simulation by this. So in another work with a company called Secure, we are trying to build our data set, but not in IoT environment, but in the communications between client and server using QUIC and HTTP3. So we are creating similar attacks within a closed client and servers environment, in one closed room environment, and we are trying to get a data set. We started this work a few months ago, and now we have like thousands and thousands of data. So for now, this data set is not public because the work is not finished yet. But maybe we will put it like a public data set in the future. But I totally agree with you that the data set is the real challenges when we work on machine learning applied to IoT devices, etc. I'm trying to, in several conferences, I'm trying to encourage people to put their data set very open. I did this in Spain, I did this in Canada, etc. And I hope that our scientific community will help us in order to put their data sets open for the public.
Okay, thank you. Thank you very much.
Thank you.
Thank you. Maybe one last question actually, because it's already 3 p.m. I know most of you you do have meetings at this time. One last question from the floor. Go ahead. Yeah, maybe as I asked the first question, let me ask the last question then. It's a more, let's say, as you talked about SDN controllers and the behavior of this kind of attacks within these 3 layers of the SDN architecture. I was just thinking about what, in your opinion, in terms of, do you think that 5G and beyond architectures, or maybe 6G also, are, let's say, integrating new security, let's say, solutions or approaches to maybe improve this stuff of different attacks actually that we can observe actually for the different kind of networks?
Yeah, thank you very much, Mahmoud, for this question. So yeah, I strongly believe that in 6G and 5G and beyond technologies, 6G and after and beyond, so when we use the artificial intelligence and various machine learning techniques in order to behave and to deal with attacks. Why? For 2 reasons. The first one, because the attacker now are using artificial intelligence to do their attacks. So I would like to thank you very much for attending this seminar.